It's going to cover rotational motion. So you're going to want to make sure that you're looking at how, change in angle, the angular velocity, the angular acceleration. You want to look at your centripetal acceleration. And if I'm writing a study guide for Chapter 7, it's going to look like this. And I'm going to double check something real quick here, because I don't think, okay, I do have a Kepler's law question on the test, and it's related to the period and the radius. So I do have a Kepler's law question on there. But we've covered Kepler's law a couple of times. You do have a problem that deals with the centripetal acceleration of an orbiting space satellite, where you're given the mass of the planet, and you want it being equal to the acceleration, the gravitational acceleration on Earth. So even though it sounds like a Kepler's problem, or it sounds like a Newton's gravitational problem, basically it's an angular acceleration problem. I'm double checking. I would look at the bucket problem. Make sure, look at that bucket example where you're dealing with a cylinder. So I would make sure on your cheat sheet to have the moment of inertia for a cylinder, the moment of inertia for a sphere, and your moment of inertia for your individual particles.
Dr. Woodblood,
Yeah.
can you pull your display down just a little so we can see the top?
Okay.
Sorry.
I'm looking to see if I've got a study guide. If I were pulling a study guide, see if I've got one in my notes here. Or here's a Chapter 6 study guide. Everybody got the Chapter 7 study guide? There's a Chapter 6 one. I'm looking to see if I got a Chapter 8 one. Kepler's laws are all planets move in elliptical orbits with the sun at one focus. This is the equal areas one, where if I'm sweeping out in the time period, I get the equals area, and that the nominal period is squared is equal to the radius, or proportional to the radius cubed. Okay, this, if I were making an exam sheet for everything that we have covered so far, So I have a chapter 6 one, and I have one that if I have everything covered so far. Okay, we good?
No, I got the rights of her. So where is it, equal sun is, I can't read that.
T squared
Oh, no, I'm saying the sun, something, and,
a line drawn from the sun sweeps out equal areas in equal time. Basically, what that is telling us, let me flip through. There we go. Basically, what that area sweep is this right here. That's the second law. That's Kepler's second law. Kepler's second law is that if the change in time here and the change in time here, the areas of those triangles are the same. The area of those triangles are the same. And the third law is that the period of the orbit is proportional to the nominal radius cubed. And that's a constant, and my constant is going to be that 4 pi squared by the gravitational constant. But we can look at our forces in terms of my centripetal force is mass times my centripetal acceleration, and my centripetal acceleration is v squared over r. So those are our planetary motion Kepler law items.
can we look at that again?
Let me put clean paper behind it because that way that paper is.
It's a little out of focus.
Can you focus?
Just a second.
Okay.
Better?
Yes.
Yes.
Okay. All right. I'm writing a study guide for chapter 7 all by itself. We did chapter 7. We did that one. I'm doing chapter 6 all by itself. I would be looking at, I'll go do it this way. So I'd be looking at that I have my linear momentum. good. I'm going to shift it up. Momentum is conserved in glancing. There is not an instantaneous thrust problem on the test. We don't have any of those on the test. But then if I have glancing blows, this figure really helps you if I have two-dimensional collisions that I can have in my two-dimensional collision type problems. So what you're looking at is you're going to make sure that you can do your head-on collisions. You want to be able to do two-dimensional collisions. You want to be able to do collisions where you're calculating the energy based on the collision. So you want to look at that ballistic pendulum problem. You know, that example for the ballistic pendulum, you want to look at that one. You want to look at if I have got a spool of yarn and I'm pulling the spool of yarn, I want to know linear distance and angular distance. You want to be able to calculate, you know, your angular acceleration, calculate your tangential acceleration. You'll want to be able to calculate a center of mass. We're actually going to do a center of mass problem here in just a little bit. And you want to calculate a moment of inertia. You want to look at the teeter-totter problem, and you want to look at the billboard problem. And I'll show you a couple other things that you'll want to look at as well. But there won't be a rocket thrust problem on there. If I were making a sheet for any exam up to this point, this is what it would look like. You have your kinematics equations at the top. You've got your Newton's laws in there. You have your coordinate systems and how you can get your vectors. You've got G. So this is just kind of going through it. This is chapters, the first chapters in the book where we started. This is Newton's laws chapters right through here. My two coordinate systems we've used all the way through. Then I get my work energy problems that we've had. There's my work, there's my kinetic energy, there's my potential energy. There's my force associated with Hooke's law for spring. There's my spring energy. There's power. This is power. There's my momentum, and my force is a change in momentum. Here is that, this is impact. And I get my elastic collisions, my momentum before is equal to my momentum after, my kinetic energy before is equal to my kinetic energy after, And inelastic collisions, I don't have the kinetic energy one. So this is impact, these are actually momentum. Then when I get down to my angular motion, there are my kinematics equations in my angular motion. There are my conversions between centripetal acceleration, tangential acceleration, and my tangential velocity. There's my torque. This is the sum of the torques. And L is angular momentum. And there's my angular momentum equation. And there's my general form for my moment of inertia. And there's my kinetic energy form with my moment of inertia. The things that are missing on this that I would now include would be I of a sphere. And I of a sphere is 2/5 mr squared. I of a cylinder is 1/2 mr squared. And my rod, if I'm doing it about the middle, I of the rod is equal to 1/12 ml squared. And if I'm doing the rod about an end, I of the rod is equal to 1/3 ml squared. I would add those to my sheet. What, you had a question?
What did you say L was?
The length of the rod?
In the,
This L?
yeah,
That L is angular momentum. That L is angular momentum.
And this is a length.
This is a length for the rod.
I'm not done with
Sneeze is there, it's just not coming.
I gotta get that in my, I gotta get the spring and all that.
Okay, I'm going to move on. How I would study for the test. Okay? Hopefully by now, you figured it out. But how I would study for the test. This is chapter 8. Okay? So I'm going to kind of go through chapter 8 here. This is chapter 8. It may not look exactly like what you have because I'm not sure if this chapter 8 is in the 10th edition or if this chapter 8 is in the 11th edition. But there's not much difference. Okay? And it doesn't really matter. It could be any physics text. It could be the OpenStax text. It could be any physics text. This is how I would study for the test. First thing I would do is go to the back of the chapter. And in the back of the chapter, there is a summary. This essentially is where all the key information of the chapter is. Okay, key information of the chapter. So things that I may want to make sure I've got included on my cheat sheets would be, there's our equation for torque, which I've already had on the cheat sheet. There are my conditions for equilibrium. Summation of the torques equals 0. The summation of the forces equals 0. Here are my relationships between my angular, my moment of inertia, and my torque. Here is my rotational kinetic energy, the same things that we've had. And then here is my angular momentum. So I've got my summary that gives me a really good place to start. The next thing I would do is I will go through here and flip through your chapter. So let's flip through the chapter. We talked about torque. Okay, that's a fundamental concept. We talked about how I can have a wheel or a valve stem or something like that. We talked about that one. Oh, if we talked about it in class, I better look at the example. Okay? We talked about it in class, I better look at the example. So I can still flip through here. And we had the swinging door. We actually kind of talked about it. We didn't really do a whole lot of problems with this one. We focused on the seesaw problem. Well, if we did a couple of seesaw problems, which we kind of did, we did a seesaw problem where we did the seesaw like this, and we did the problem where we had the two guys on the window, on the scaffolding outside the window, and we looked at the forces and the torques on that one. So this would be an example that I probably would want to go through and make sure that I've got that one covered. We talked about center of gravity, and we're about to do a center of gravity problem. So I think I might want to review my center of gravity. Okay, I think I might want to review my center of gravity. We didn't necessarily do one that looked like this, but you did have a homework problem where you kind of took the legs and the body and you calculated the individual centers and then did an overall center. So you kind of have a place to look. So that one may not necessarily be as one as I would look at so much. I might look at this one because it helps me with my diagram and drawing out my diagrams for my problems. The ladder problem is notorious. It's out there everywhere. And that's the one that incorporates friction. So I might want to review the ladder problem. This is a different version of the seesaw problem. But then we started talking about rotating objects, and we started calculating moments of inertia. We did the baton problem, so I might want to look at it again. And we did it both directions. Right? We did it this way as we're going around, and we did it this way as we're going around. This is your table with your moments of inertia. So if there's one that you want to double check on for those moments of inertia, this is your diagram in the text for it. I would definitely look at my weld problem. Definitely look at my weld problem. Look at how that weld problem is in there. And there's the solution to the weld problem. It's on the next page. We have the ball rolling down an incline. These are your blocks and pulleys. And these are going to be similar to the weld problem. Then we had our angular momentum. We did the ice skater problem. The book uses the spinning stool problem, but it's a similar problem. and the Terror Go-Round. We've done several things with the Terror Go-Round. So I would definitely look at the example for the Terror Go-Round.
Which is 33.
Well, it depends. It's the merry-go-round problem. It's example for the merry-go-round problem. I don't exactly, again, I'm not sure if this chapter 8 is the 11th edition version or the 10th edition version. There really isn't that much difference between the two versions of the text. It actually comes out in more a little bit of the formatting than it does anything else, and there's different questions in the back of the chapter, but they're very, very similar. So that's how I would study for, and that's how I did study for my general physics exams. You do have, if there's a concept that you're having trouble with, the videos, I'm going to try and get this video up right after class, provided I don't have, a line out the door, which is usually what happens. But I would get that out there. But you also have access to the OpenStax text. So let me kind of go, and this is also a really good tool. Let me get the computer going. We'll switch to the computer. And I'll show you a couple of nice things. So if I go just anywhere online, pick whichever one you want to use, it'll get there. So we get there, and I think I'm pretty sure I have the link in Blackboard as a resource, but you can do this, and you can usually do this for any other class. So this is another resource for you for any other class. It's OpenStax, and OpenStax is open domain, right? They have, this part of their grant, they have made any of these textbooks available, and they're by different subjects, okay? So if you're having trouble in your math class, you're having trouble in a variety of different things, they're there. So we're going to go over to science just so you guys have a chance to see a variety of the texts that are available that make it easy for things that are in here. But there's chemistry, biology, anatomy. They also have it in different languages. So if English is not your first language, this may be a resource for you, okay? And there's the difference between college physics and university physics, or general physics and engineering physics, is we use algebra to explain the concepts for general physics. We use calculus to explain the concepts for engineering physics. But for physics 1, it's not much different. So you can open it up. You can download it, you can save it as a PDF, you can use it, but view online. So if we're going to go in here, and we're going to go down here to, let's go ahead and statics and torque. And we're going to go in here and look at the first condition for equilibrium. And if you do that, they've got the same types of figures. And because of how they group it, and how they do it, it's a little different, and if our book isn't giving you the explanation you need, another textbook might. It's very similar to, sometimes I can explain it and everybody understands it, and then I come in the next day and I explain it slightly differently and it doesn't click with anybody. So, you really get, you can use it to your advantage. So this is the sum of the torques. Now, what's really nice, so now they're using a hockey stick, which is a different one. They give you ways to go in and connect to other stuff. So this one does have a connection directly to some simulations. So we can look at there. So if I go over here, and let's go to rotational motion, and we're going to go down here. We're going to do rotational inertia, so this is moments of inertia, so they're going to use the bicycle. There's a similar problem, similar diagram to what we have in our book, and there's our calculations for a variety of things. They give you a problem-solving strategy that isn't in our text. So they give you a problem-solving strategy that's not in our text. They give you a diagram that's got a few more things in it. Okay, here's our merry-go-round. So there's the merry-go-round, and all of a sudden torque is an analog, and it gives you a problem and it hides the solution. So you can actually go in and look in this book and say, okay, I'm looking at this, and I can say show solution, and it'll give you the solution to the problem. And then you can do a variety of things. So if you come down here to problems and exercises, they've got some problems there. They've got other additional problems. So and it refers back. So there's some other problems that you can go to and say, okay, I don't like the problems in my book. Let me go look at some other books to help me. So you do have access to OpenStax, and then as you saw, there's more than just the physics text out there. There's a bunch of different aspects to it. Okay, so that might help, might give you something, some other places to go and utilize. So I want to do a center of mass problem. Okay, we'll actually combine. Let's see. We'll do that one. Okay, we'll do that one. This will combine a couple of things. All right. We're going to start with, am I got on the screen? No. I thought I pushed the button, but you never know. Okay. In Argentina, they use, instead of a lasso or a lariat, they use a device that kind of looks like this. It'll have 3 balls on it, and they're usually attached with rawhide. So I've got my 3 balls attached with rawhide. What we're going to want to do is what they do is they'll swing it like a lariat and it'll wrap around the cow's feet. I'm going to have this one placed at 4, 5. I'm going to have this one placed at 3, -3, and I have this one placed at -4, -5. This is going to have a mass of 2 kilograms. This has a mass of 1 kilogram, and this has a mass of 3 kilograms. So we've got this lovely. What we're going to ultimately do is we're ultimately going to calculate the moment of inertia about the origin, about the y-axis, and about the x-axis. But the first thing I'm going to do is find the center of mass of the system. Okay, so the first thing I'm going to do is find the center of mass of the system. Then we'll go back and do the moments of inertia. So if I'm doing the center of mass, the center of mass is going to be the sum of mx divided by the total mass. And the center for y is going to equal the sum for each individual y divided by the total mass. So I'm going to need the total mass. So let's do that first, because that's going to be easy, right? The sum is going to be 3 kilograms plus 1 kilogram plus 2 kilograms. It's going to give me 6 kilograms. So I've got my total. It's going to make life really simple. So if I'm going to do the x, it's going to be divided by 1/6, because that's what's out there. I'm going to take my first mass, which is 2. I'm going to multiply it by its x, which is -4. I'm going to take the second one. I'm going to do 3. I'm going to take its x, which is 4. And I'm going to do the third one, which is 1. And I'm going to take its x, which is 3. So this is minus 8, this is 12, and that's 3. So 15 minus 8 is 5, right? If I've done my arithmetic right. This becomes 5/6. It's gonna be 7?
I thought it was 7.
Okay. So I said if I did my arithmetic right, that's why showing your work helps. Because if you did that on the test and you showed your work, you're gonna lose a little bit of points, but you're not gonna lose all the points. Then for y, it's gonna be 1/6. I'm gonna have 2 times my minus 5. I'm going to have my 3 times my 5, and I'm going to have my 1 times my minus 3. That's going to be minus 10, that's 15, and that's minus 3. So that should be 2, right? 13, 15 should be 2. So it's 2/6. And 2/6 we know really well is equal to 1/3, which is going to equal to 0.333. So the center of mass of our system, if I do 7/6, that's actually 1.17. So the center of mass is going to be in the x direction, it's going to be somewhere over here. And we're up, so that's where my center of mass is going to be for this system.
I can't see.
If I had it, I don't have it to scale, right? I don't have it perfect. But my center of mass is going to be right about there. So my center of mass is going to be at it's 1.17.33. Now, if I am doing my moment of inertia, remember my moment of inertia is going to be the sum of the individual mr squareds. So I'm going to need the r squareds. So if I'm doing it about the origin first, okay? Doing it about the origin first. So we're going to look at the moment of inertia as it goes around. My r is to the origin. So this r is going to be the square root of 4 squared plus 5 squared. If I do that, this is like 6.4. This r is the square root of 3 squared plus minus 3 squared. And that should give me like 4.2. Let me double check it. For some reason that just doesn't seem right, but it could be just me today. Yep, 4.2.
Can you raise it up?
Okay, just a second. Like that. And this one should be 6.4. Because it's 4 squared plus minus 4 squared minus 5 squared. So my r is 6.4, my r is 6.4, my r is 4.2. If I'm going about the origin. So it's going to be the sum of the mr squareds. So this mass is 2, 6.4 squared, plus this mass is 1, 4.2 squared. That mass is 3, 6.4 squared. This will give me 222.4 kilograms meters squared. And this is about the origin. I wish I could think of the name, it's driving me crazy. The lariat. It's not a lariat, but it's the gaucho's lariat. Okay, now if I want to do it about the x-axis, I want the r to the x. Okay, so you're looking at the r to the x. So if I'm going to do it about the x-axis, it's going to be mr squared. It's going to be 2, but I'm using how far away it is from the x-axis. And this one is minus 5 squared. Then I've got my 3, 5 squared, plus my 1, 3, minus 3 squared.
Is that 5 or 3? 5, 2?
This is 2 times minus 5 squared, 3 times 5 squared, and 1 times minus 3 squared. Because I've got to go away from the x-axis. If I do this, this equals 134 kilogram meters squared. Because this is 2 times 25 is 50. 3 times 25 is going to be 75. So that's 125. And then I get 9 for this one. So 9 plus 125 is 134. I'm going to do it about the y-axis. My r is like that. I'm doing it about the y-axis, the r is like that. So if this is about the x-axis, and about the y-axis, it's going to be the sum of the mr squares again. So I'm going to have the 2, except it's at minus 4 this time. I'm going to have the 1, and it's at 3 this time. And I'm going to have the 3, and it's at 4 this time. So this gives me 2 times 16, 1 times 9, 3 times 16. And if I do that, that works out to be 89 kilogram meters squared. Okay, just for review.
When I was looking at the example in the book, it was giving me the answer, and I'm trying to figure out how they got it. So that makes a difference.
All right, so just as a review, we're gonna start with a disc. It's got a radius, and the radius is gonna be 0.25 meters. It's starting at rest. And it's gonna reach an angular velocity of 3 radians per second. And it's gonna do that, and the time is gonna be 0.03 seconds. So we got a disk that starts from rest. We wanna calculate the change in angle. We wanna calculate the angular acceleration. We want to calculate the centripetal, the tangential, and the total acceleration. We want to look at the number of revolutions and the tangential velocity at our 0.03 seconds. So omega is going to equal omega initial plus alpha t. We need our alpha, and our alpha is omega divided by t, and so that's going to be our 3 radians per second divided by my 0.03 seconds, and it's going to give me 100 radians per second squared. My tangential velocity, I don't have to do this in order, is r omega. So I'm going to do my 0.25 times my omega, which is 3 radians per second, and that's going to give me 0.75 meters per second. My centripetal acceleration is r omega squared, 0.25 times my 3 radians per second squared, 2.25 meters per second squared. My tangential is r alpha, so it's 0.25 times my 0.75. And that one gives me, no, r alpha. I wrote the wrong thing in there. This is my 100 radians per second squared. And that's going to give me 2.25 meters per second squared. No. I'm looking at the wrong spot. 25. Then A is going to be the square root of 25 squared plus 2.25 squared. Gives me 25.1 meters per second squared. My change in angle is going to be omega t plus 1/2 alpha t squared. That's 0, so it's going to be 1/2 my 100 radians per second squared times my 0.03 seconds squared. And that gives me 0.045 radians. And if I want it in terms of revolutions, the change in angle 0.045, 1 revolution per 2 pi, and that gives me 0.007 revolutions. Do a teeter-totter problem. I have a person that is 1.5 meters away from the fulcrum. And this person has a weight of 50 newtons, so that's force. We want to know where this person has to stand, and this person has a force of 45 newtons. And I want to know the distance, and I want to know the force that the fulcrum has to apply. So I want to know both the force that the fulcrum has to apply, and I want to know the distance. So in this case, the sum of the forces has to equal 0, and the sum of the torques have to equal 0. So if I look at my picture, I have the force that's being applied upward, which is what I want to find out. I have the force of the first person and the force of the second person. That all has to equal 0. So the force is going to equal 95 newtons. Sum of the torques, if I go this way, remember this direction is positive, this direction is negative. So if I'm going around this direction, that's positive, that's going to be 50 newtons times its lever arm, which is 1.25. This side's going the wrong way, so it's going to be negative, and I got my 45 times the distance has got to equal 0. This is 50 times my 1.25 is equal to 45D, and that becomes 50 divided by 45 times 1.25 is going to equal D, and that equals 1.39 meters. So hopefully this gets you ready. I would go back to the 3 chapters, look at the examples, know what examples we kind of did over and over again. And I think you're ready. Next week we start our fluid stuff, and then we'll do our thermodynamics the last week. And the final in here is Monday morning, 8 a.m. of finals week. The final is already at the testing center for those that need to avail themselves of that for whatever reason. And the final is set up so that you have to take it between the Wednesday and the Friday of that week after Thanksgiving. So if you're taking it at the testing center, it has to be done before the final time, in order for me to get it back and get it graded and all that good stuff.
Guys, the test, cell phones.
Do what?
Oh, I'm talking to them, sorry.
Okay, all right. Okey-dokey. And you have to email me if you're taking the test at the testing center, so I can get the right paperwork in the right spot.